Today we're going to cover internal resultant loads. So let's look at an example. Determine the resultant internal loadings on the cross section through point C. Assume the reactions at the supports A and B are vertical. Alright, so we're focusing here at point C. So the first thing that we need to do is we have a distributed load. So we need to determine the magnitude of our distributed load and the location over the entire body. So to find the magnitude of a triangle distributed load, it's just the area. So in this case, 1/2 base times height, where our base is this 3 meters and our height is 3 kilonewtons per meter. So we end up with 4.5 kilonewtons. How do you know where it's located? We know that the centroid of a triangle is located 1/3 from its base. So if you look at the thick or what I like to call fat base, you move 1/3 over. So because this total distance is 3 meters, 1/3 over is just 1 meter. So the 4.5 kilonewtons would be 1 meter from point C. Alright, so now that we've determined our magnitude and location of the distributed load, we have two unknowns, AY and BY, and we want to find those two unknowns before we can determine the internal loadings at point C. So to find the unknowns, I do the sum of the moments about point B, and that will give me AY. Or I could do the sum of the moments about point A, and that will give me BY. So when I do the sum of the moments about point B, I can ignore BY because it falls on B. But then AY causes a clockwise rotation, so it's negative AY times 4 meters plus this 6 kilonewtons, it causes a counterclockwise rotation, times 3.5 meters plus 4.5 kilonewtons, it causes a counterclockwise rotation, times 2 meters, so it's 1.5, and remember it's 1 meter from C, so there's another 0.5 here. So in the end, once we solve, we end up with AY is 7.5 kilonewtons. So I got positive 7.5. That means the way that I drew AY originally is correct. So it's going to be 7.5 kilonewtons pointing upward. From that point, now that we found AY, I'm going to cut the beam. So pretend that I cut the beam in half at point C. And I could either choose to look at to the left of the cut or to the right of the cut. But I'm going to choose to look to the left because I'm only dealing with two forces, AY and 6. Actually, either side would be only two forces, but we haven't found BY yet. So I'm going to look to the left. So here we have it. And it's like I said, pretend that you're cutting the beam at point C. And I draw my internal loading, so I have NC, VC, and the moment C. Now you can draw them randomly. I chose to draw it to the right, downward, and counterclockwise, but it doesn't matter which way you draw them. In the end, your signs will come out correctly. So first I solve for NC. Because there's no other X force or X component, we know that NC is just equal to 0. Then I solve for VC. So I write the sum of the moments, or the sum of the forces in the Y direction. I have positive AY minus 6 minus VC. So I get VC equals 1.5 kilonewtons. Because it's positive, it means the way that I drew VC originally is correct. So VC is 1.5 kilonewtons pointing downward. Then I proceed to solve for the moment. I do the sum of the moments about point C. And here I have MC, I'm going to have the 6 kilonewtons and the AY causing a moment. So MC, it causes a positive rotation because it's counterclockwise. Then I have AY, which would cause a clockwise rotation, so it's negative AY times 1 meter plus 6 kilonewtons because it's counterclockwise times 0.5 meters. So this way I end up solving for MC, and MC equals 7.5 kilonewtons times meters. And because it's positive, it means that the way I drew it is correct. So it's at 4.5 kilonewton meters counterclockwise. So we have just found all of our internal loadings, NC, VC, and MC. And I like to write their directions, their magnitude, and then their direction separately, just because it helps me, but you can do it however you'd like to. It's just really clear this way when you write which way they're pointing or rotating. So we're going to continue with this example, and here determine the resultant internal loadings on the cross section through point D. So we just found point C, but now they want it through point D. So the first thing we want to do once again is to determine the W, which we did that, right? We did that already. We determined W, 4.5 kilonewtons, 1 meter away from point C. So we already found AY, but now I want to find BY because it'll help me find my internal loadings at point D. So I do the sum of the moments about point A. Yeah, this should be point A, sorry. So if I'm doing the sum of the moments about point A, I can ignore AY because it falls on that point. Then I have BY because it's counterclockwise. So positive BY times 4 meters minus 4.5 because it's clockwise times 2 meters minus 6 kilonewtons because it's clockwise times 0.5 meters. So I end up with BY equals 3 kilonewtons, and because it's positive, it means that I drew BY correctly. So it's 3 kilonewtons upward. Now another way you could have solved for BY is from the first part we solved for AY. So instead of doing the moment about point A, you could have actually just done the sum of the forces in the Y direction. Because you know AY from part 1, you know 6, you know 4.5, so then your only unknown would be BY, and you could solve for that easily. So now that we found BY, they ask us to determine the internal loadings at point D. So here I need to decide, do I want to consider everything to the right or to the left? Well, I'm going to consider everything to the right because the triangle, the distributed load, is a simple triangle. Whereas everything to the left, you have this triangle, but it ends up being a triangle with a rectangle. So it just becomes too complex. So we pick everything to the right of D. So we previously determined the overall weight to be 4.5 kilonewtons, right? But now we want to determine the weight just for part D to B. And the way we do that is by just taking ratios. So I do the height of the overall triangle over the base of the overall triangle equals the height of the smaller triangle over the base of the smaller triangle. So height 1 is 3, base 1 is 3, and then height 2 is unknown, and base 2 is 1.5. So we end up with H2 equals 1.5 kilonewtons per meter. So this is 1.5 kilonewtons per meter. So that means we can find our distributed load for the little triangle. This little triangle by just doing 1/2 base times height. And we just determined that the base is 1.5, the height is 1.5 kilonewtons per meter. So we end up with W2 equals 1.125 kilonewtons. Where is it located? We know that the centroid of a triangle is located 1/3 away from the fat base. So 1.5 times 1/3, it's 0.5 meters away from point D. Alright, I hope that kind of makes sense. So now we want to determine the internal loading. So we cut the beam at D, and we look for everything to the right. Just because it's more simple, right? We don't have to consider this weird load and other forces. We just have to worry about W2 and BY. So I draw in my ND, my VD, and my MD, and I drew them arbitrarily. You can draw them any way you'd like to. There's no other x components, so ND equals 0. for VD, I do the sum of the moments in the y direction, so I end up with By minus W2 minus Vd. So VC, this should be Vd. I apologize. So Vd equals 1.875 kilonewtons, and it's positive, so it's downward. Now, we could have drawn Vd upward originally and solve for it that way. So then we end up with Vd plus By minus W2. And here you end up with Vd equals negative 1.875 kilonewtons. So you end up with a negative. That means that this direction that I drew it is not correct. It should actually be the opposite direction. So once again, we end up with Vd is 1.875 kilonewtons downward. That should prove to you that no matter which way you draw it to begin with, you will end up with the correct number in the correct direction. Let's look at MD. So sum of the moments about point D, you end up with By times 1.5 minus W2 times 0.5 minus MD, and that ends up with MD equals 3.94 kilonewtons times meters, and because it's positive, it's correct the way that I drew it, so it is going to be clockwise. And here I'll show you if I drew it the other way, do the summation. In this case, MD is rotating counterclockwise, so it's positive MD, and still you end up with MD equals negative 3.94 kilonewtons times meters. So that tells you that it shouldn't be counterclockwise, it should actually be clockwise. And that should prove to you again that no matter how you draw it, you should end up with the correct direction and the correct magnitude. And here we go. We have all of our answers. And some things to keep in mind. Remember how you're drawing the loadings. Pay attention to your signs. And always write the final direction that it points in. So either redraw your free body diagram with the correct directions, or just write, is it up, is it down, is it clockwise, counterclockwise. I hope that helps you guys.